Welcome to this explainer. If you're sitting in chemistry or physics class wondering how you might actually help save the world one day, well, you're in exactly the right place. We're diving right into a seriously mind-bending concept today, taking regular, everyday water and ordinary sunlight and transforming them into zero-emission green hydrogen fuel. I know, it sounds a bit like science fiction, right? But it's very real and very cool chemistry. Here's our roadmap for today. We'll be covering 1. Mimicking natural photosynthesis. 2. The electron's mountain climb. 3. Splitting water step by step. 4. Why titanium is ideal. And 5. Boosting future efficiency. Let's get right into it.
Section 1. Mimicking natural photosynthesis. You know, nature figured out how to use solar energy billions of years ago. Today, we're basically stealing a playbook right from plants to create clean, human-made energy.
Take a look at how perfectly the natural world lines up with our technological one. On the left, you've got natural photosynthesis, taking sunlight and plant materials to make oxygen and biological energy. Simple enough. On the right, we have artificial water splitting. It acts just like a mechanical leaf. It uses UV sunlight and a special semiconductor catalyst, specifically titanium dioxide or TiO2, to create green hydrogen and oxygen. The end result? A super clean, powerful fuel with absolutely zero carbon emissions. Literally none. Section 2. The electron's mountain climb. To really understand how this mechanical leaf works, we need to shrink down to the microscopic level and meet the true hero of our story. Meet the electron. Right now, before any sunlight hits it, our electron is just kind of chilling at the bottom of a metaphorical valley. In chemistry, we call this valley the valence band. It's resting there, totally unexcited, just waiting for a massive rocket boost of energy to kickstart its journey. And here comes that boost. When the cosmic energy drink of the sun arrives, incredible things happen. Those incoming sun rays hit the titanium dioxide and excite that resting electron. It gives the electron the exact amount of power it needs to leap out of the valley, the valence band, or VB, and shoot all the way up to the mountain peak, which is the conduction band, or CB. Now notice that when the electron makes that huge jump up, it leaves behind this positive void at the bottom. We call that a hole, or H+.
But here's the thing. This jump isn't exactly effortless. The space between the valley and the peak is called the band gap. Think of it as the exact height of the mountain the electron has to clear. For a specific type of titanium dioxide called anatase, this mountain is about 3.2 electron volts high. The incoming sunlight has to pack enough punch to push the electron completely over this hurdle. If it doesn't, well, the whole process just won't start.
Section 3. Splitting water step by step. Because getting that electron up the mountain is really just phase 1 of 3 chemical stages. So, once our electron is at the peak and that hole is left down in the valley, this beautiful chemical dance begins. Step 1 is what we just talked about, light absorption. The photon hits, the electron jumps. Easy. Step 2 is water oxidation. Down in the valley, those positive holes we left behind, they get right to work on the water molecules at the surface of the catalyst. They oxidize the water, literally ripping it apart to release pure oxygen gas, or O2, and some leftover protons. Then comes step 3, hydrogen evolution. Up at the mountain peak, our excited electrons meet up with those leftover protons. The electrons reduce the protons, snapping them together to form our ultimate prize, pure hydrogen gas, H2. So water goes in, and oxygen and hydrogen fuel come out. It's absolutely brilliant. But hold on a second. It isn't always that smooth. What happens if our electron gets tired and actually falls back down the mountain before it can connect with a proton to make hydrogen?
Well, this brings us to the absolute biggest threat to this entire process, electron-hole recombination. And it's exactly what it sounds like. The excited electron just drops right back down into the positive hole it originally left behind in the valence band. If they recombine, all that energy is just lost, usually as heat. We completely lose our chance to make green fuel, and our efficiency absolutely plummets.
So how in the world do chemists stop the electron from tumbling back down? They add co-catalysts. Materials like platinum, nickel, or ruthenium are deposited right onto the surface of the titanium dioxide. You can think of these co-catalysts as specialized climbing gear, or maybe a safety net right at the top of the mountain. They catch those excited electrons, trapping them at the peak so they can't fall back down the hole. This safely stores the electrons exactly where they need to be to pump out high volumes of hydrogen gas, massively, and I mean massively, improving our efficiency.
Section 4. Why titanium is ideal. Out of all the elements on the entire periodic table, why is titanium dioxide the absolute star of this water-splitting show?
Honestly, titanium has an absolute dream resume for a green energy catalyst. First off, it's incredibly abundant and low cost. You can actually find it in everyday things like white paint and sunscreen. Second, it is completely non-toxic. Third, it's highly chemically stable. That means it won't easily corrode away while it's just sitting in water under bright UV sunlight. Fourth, it is wonderfully environmentally friendly. The whole process produces zero CO2 or harmful byproducts. And fifth, it's totally reusable. You can recycle it over many, many water-splitting cycles. It's cheap, safe, and tough as nails.
Section 5. Boosting future efficiency. Because while titanium dioxide is amazing, there are definitely still some major technical hurdles to clear before large-scale green hydrogen completely replaces fossil fuels.
Right now, the biggest hurdle is that normal titanium dioxide mostly only absorbs UV light to get its electrons over the mountain. But here's the catch. UV light makes up a tiny, tiny fraction of sunlight. We're basically wasting all that beautiful, visible light. To solve this, scientists are doing something called doping the titanium. That means they mix in tiny amounts of elements like nitrogen, silver, or iridium. Or they create heterojunctions, layering it with materials like cadmium sulfide or graphene. Doing this tunes the titanium's properties, effectively lowering the height of the mountain, so that regular, visible sunlight can excite the electrons. This extends absorption and gives a huge boost to efficiency.
So I want to leave you with this thought. Could customized, visible light-absorbing titanium completely power your future home or your future car with absolutely zero carbon emissions? The answer is a resounding yes, and we're getting closer every single day. If you're a student mapping out your future right now, fields like green engineering, materials science, and chemistry are where you can literally invent the solutions that save our planet. You could be the one who finally unlocks the perfect artificial leaf. Thanks so much for exploring the electron's incredible mountain climb with me today, and I'll catch you on the next explainer.